In previous lecture, we talked about the free electron screening, and it is a basic assumption that ions attract electrons, and the electron cloud screens out the static potential of ions. And from this consideration, we define that electronic susceptibility and also dielectric function. And here we in this time we will study further. We will solve the Schrödinger equation, not the Poisson equation, because the screening effect in the free electron we solve the just only the Poisson equation, which is the classical electrostatics. But in quantum mechanics, we should solve the Schrödinger equation, and the Schrödinger equation solution, we call it is Thomas-Fermi screening. It is Thomas-Fermi screening. Just on either a Poisson equation is the solution for the classical electrostatics, and also basically we should solve the Schrödinger equation. Here the potential is total potential composed by the external potential by ions and also induced potential by electron cloud. And the Schrödinger equation is that h bar square of 2m Laplacian psi I minus E phi. Here it is the potential phi I equal to epsilon I psi. The minus sign in potential means that it is a trapped potential, and therefore we should solve the electron density in quantum mechanical calculation. And to solve this problem, we should have the several assumptions. And let's assume that the first assumption is that phi is a slowly varying function of R, and the phi R is a slowly varying function of R. It implies that this potential is not strongly dependent with R, but here the epsilon k is that they have the kinetic energy. H bar square k square over 2m is kinetic energy, and potential energy E phi r. This is a local. The potential is very localized. Here, this first term is that the free electronic kinetic energy, and second one is that local potential. It is total local potential, and it is a right assumption because the electron clouds, the Coulomb potential reaches to the very far and also very sharp potential near the ions, and but the electron clouds screens out, and the potential it makes that slowly varying function, and I will see later in more detailed functional form of the potential. And also, and the second assumption is that the momentum is small comparing with the Fermi momentum. It means that it is a linear response of electronic susceptibility. and the momentum is small. And basically, the Fermi momentum is very, very large in comparing with, because we think about free electron momentum is that the free electron kinetic energy is the metallic system, but in our case, and the screening effect itself is very localized electronic cloud near the ions. It means that momentum is very small. Yeah, momentum is not free comparing to the Fermi momentum, but just only the stationary. We basically we already solved the Poisson equation, and the Poisson equation problem is electrostatics, not free electron. And the free electron in metal, the highest energy level is very important, and the level is that the Fermi momentum. But in the Thomas-Fermi, in the Fermi screening, it is a screening effect problem, and it is kind of stationary state of electron. It is localized near the ions. That's why the Q vector is very small comparing to the Fermi momentum. It is a two assumption is reasonable. And in this case, let's consider for the electron density. Let's write down is 1 and 2, and also let's calculate electronic number density. The first electronic number density, we call it is dk over 4 pi cube. 4 pi cube means that 2 times 2 pi 2 pi cube. It comes out that 2 means that it is a spin of up and down to spin degeneracy, and it is a momentum integration. Here the Fermi function describes the population of electron, and therefore the momentum integration of the whole of the Fermi function, it gives rise to the carrier density, electronic density. Then here it is a dk over 4 pi cube, and the Fermi function is that exponential beta epsilon minus mu plus 1. In real, because energy is written like this, and this Fermi function can be written down dk over 4 pi cube and 1 over exponential and beta. Energy is that h bar square k square over 2m minus potential term and minus chemical potential plus 1. It is that real Fermi function. And in this case, the induced charge density is that we can think that uniform positive background and induced charge is that E and 0 is the electronic charge density of uniform positive background. It is a positive ionic charge, and minus electron, it is minus electron, and it is basically the total charge total charge can be composed as the local ionic charge and negative electrons. And therefore, here in this case, N0 means that number density, N0 is number density or positive background here. Number density of positive background. Then N0 is that there is no electronic potential. Therefore, it can be write down the k over 4 pi cube exponential and beta only kinetic energy term h bar square k square over 2m minus mu plus 1. It is only positive background. Positive background charge density, and therefore, and also we let's assume that the induced charge can be write down minus E. Then here NR, we assume that N0 mu plus E phi minus N0. And it is just only assumption. And here we know that it is that NR, and here E phi, here NR is assumed that N0 and the potential, and this potential is that the chemical potential plus potential, and chemical potential plus potential is that in real space total potential, then we call it is NR. We call it is just like assumption, and it is a nonlinear Thomas-Fermi theory. Here, it is just assumption for the nonlinear Thomas-Fermi theory. Then we already assumed that phi is a slowly varying function with R, and therefore we have the approximation, and here this induced charge can be calculated minus E. Here this NR is written like this, and it is mu is a variable. Mu is variable, and also this potential is a slow varying with R. Therefore, we can think about that this potential is not sensitive with the variation of mu. Therefore, we can write down it is that it is a functional. The first term is that N0 mu, and also second one is that the E phi R is not sensitive with mu, and the first derivative N0 versus mu, it is plus and so on, and we only think about that first order approximation, and minus N0R, and basically here this N0 can cancel with each other in the first term. Therefore, here it is minus E square phi R, and phi partial N0 and partial mu. Then it is that from the induced charge means that it is chi q and phi q from the above definition, from the previous lecture definition, and in previous lecture we talk about that it is a definition. And anyway, electronic susceptibility is that for a given phi, for a given potential, and it is induced charge, and therefore when you compare with each other, and also this minus c square and this one is chi. Therefore, it is chi q is that minus e square partial n0 partial mu. It is independent of q. And also, it gives rise that by changing the chemical potential, the ionic charge density variation gives rise to the electronic susceptibility, and it makes that the response, linear response. And also, then the way in real situation, there is an ionic potential in this side, and if we think about that, these ions make that increase of chemical potential. It makes that the charge density variation, because this charge density n0, and it is natural, because when you think about it, one additional, one depletion of the positive ions, it makes that charge density variation. And therefore, and because it is electronic susceptibility, and we know that epsilon q is that 1 minus 4 pi over q square chi, then it is that 1 plus 4 pi e square over q square partial n0 partial mu. Then let's denote that here k0 square, let's denote by the 4 pi e square partial n0 partial mu. Then this epsilon q is that we can write down 1 plus k0 square over q square, and it is generally uses in here it is, we call it as a Thomas-Fermi wave vector. Thomas-Fermi wave vector. Thomas-Fermi wave vector describes the variation of electronic variation of charged ions, makes that it depends on the variation of charge density of ions, and also it also gives rise to the epsilon in the dielectric function. And then by from this interpretation, we should let's think about the real potential form. In real potential form, in Thomas-Fermi screening, because the ion makes that charged particle ion makes that Coulomb potential, and that the external potential by point charge ion. And for simplicity, let's think about only single ion, whether here the phi external potential can be written down Q over R, Then previous lecture of the Fourier transform of Poisson equation, we calculated that q square phi r external r is that 4 pi rho external q. Then therefore it is not r but q, and the phi external q is that 4 pi q square, and induced charge, let's denote that it is total external charge q. Then it is basically this Fourier transform comes from the Poisson equation, and the Fourier transform of Poisson equation in real space phi r, the real space potential, Coulomb potential, becomes this momentum space Coulomb potential like this. And therefore it is by using this, the total potential in metal is that phi q is that from the previous study, and 1 over epsilon q, and phi external q, and external ionic potential dressed by the by the dielectric function is the total potential, and it is that 1 over 1 plus k0 square over q square. Here k0 is the Thomas-Fermi wave vector, and also phi is that phi external potential is that 4 pi q over q square. Therefore it is that q square plus k0 square and 4 pi q. It is the total potential in metal. And here, then it is momentum space phi, but let's make the Fourier transform of this one, and this potential is the total potential in and the momentum space, and we should make a Fourier transform. Transform of phi q, then it becomes the phi r in real space potential, and it comes out dq over 2 pi cube exponential I q dot r, and phi q is that integral dq over 2 pi cube exponential I q dot r, and also 4 pi q over q square plus k0 square. It is the Fourier transform of the total potential in real space. Then the solution is that I will write the solution is that q over r exponential I k0 r minus not I but minus k0 r, and it is exponential decay. Here we call it as a Yugawa potential. Yugawa developed the theory, the interaction between the proton and neutron, and the proton and neutrons, because neutron is a charge neutral, there is no Coulomb interaction between the proton and neutron. But in the interaction mediated by the pion, and the theory of pion was developed by the Professor Yugawa. And actually, this exponential behavior, then Q of R is the typical Coulomb force, and exponential decay, it means that significant decay of interacting potential. It means that the very short range potential, it screens out very rapidly, and therefore we call Yugawa potential is the screen Coulomb potential. Screening Coulomb potential. In previous lecture, we studied for the Jalin model, and the Jalin model assumes the independent electron approximation, and we only think about that the interaction can be ignored in overall space, and it is reasonable because the real potential in solid and screens out rapidly because of the Yugawa potential, and this screening it makes that very short range potential, and therefore it is very reasonable for the Jalin model. And here I will prove that this Yugawa potential is a right potential in solid, and let's prove that this. And we will choose for the step 1. Step 1 is that we will make a Fourier transform of central potential. Fourier transform of central potential. And in spherical coordinate, we let's denote that it is not vector r, but it is only radial function. And also because we should know that exponential I q dot r, here q dot r is that here qr cosine theta, and also the volume here, the Fourier transform of the real space potential can be transformed like momentum space potential, and it is that this integral dq over vr, not v here, vr, and exponential iq dot r. Then it is that phi equal the range from 0 to 2 pi d phi, and in the radial function 0 to infinity to r square vr dr, and also theta is that from 0 to pi, and r square sine theta exponential I qr cosine theta d theta. Then it is that 2 pi 0 to infinity r vr dr, and also here let's calculate this one as a star. Then star can be written down as that let cosine theta equal t, then dt equal minus sine theta d theta. Okay, then it is that integral, because minus and the integral region and can inverted from pi to 0. At pi it is minus 1, at theta equal 0 it is t equal 1, and this exponential I qt dt. Then it is that I QR exponential I QR t equal to -1 to 1, then it is that it is that here exponential I QR minus exponential I QR. Therefore, it is that 1 over I QR and 2 sine QR. Therefore, here this term is that I QR 2 sine QR. Okay. Then it is that here 2 4 pi yeah 4 pi over IQ here I square. Therefore here from 0 to infinity 0 to infinity R VR R sine QR R sine QR VR. I'm sorry, here it is a 2i. Then I cancel with each other, and therefore it is IQ. Is IQ. IQR, and also it is I cancel with each other, therefore this I is ignored. I cancel. Yeah, okay. DR. Then the here and because it is Fourier transform of the potential, and let's take a step 2, and let's because we calculated that the potential of real potential is that is kind of Yuga potential, and here in the phi r is write down the q of r exponential minus k0 r, and let's replace that. It gives rise to the momentum space potential. Is that here when we substitute this one to here, this VR, and 4 pi over q integral 0 to infinity r sine qr, and VR is that q over r exponential I k0 r dr. Then to calculate this, let's have a trick. The one trick is that because in the sine qr can be write down for the imaginary part of the exponential IQR, because exponential IQR has the exponential IQR is that the cosine QR plus I sine QR. Therefore, and the imaginary part, the sine QR is the imaginary part of the exponential IQR, and therefore, and here it is integral to r infinity to r it is and r cancel with each other, and therefore 4 pi q and integral 0 to infinity imaginary part of the exponential I qr and exponential, I'm sorry, it is not I but minus k0r minus this exponential is a real function, and anyway, and here this can be calculated, and it is 4 pi q over q. Then imaginary part of this integration is that iq minus k0 over exponential iq minus k0 r, and r from the 0 to infinity. Therefore, it is that 4 pi q over small q, and imaginary part, because in the infinity it goes out because minus k0r, and at r equal to 0, and it is 1, therefore it is minus 1 iq minus k0. Then it is that 4 pi q over q, imaginary part, it should be rationalized, and the k0 square plus q square, and also here k0 plus iq, because when we make a complex conjugate, then because we only take the imaginary part, and here 4 pi q over q, and also k0 square plus q square q. Therefore, it is that 4 pi q over k0 square plus q square. It is a potential in momentum space, and the potential in momentum space. Therefore, and we can say that this in real crystal, if there is if external potential becomes ionic potential, becomes a Coulomb potential, Q over R, then in real space, total potential becomes Q over R, and the exponential minus K0R. It is a Yuga potential. That is the main conclusion. And here, because the potential screens out very rapidly because due to this exponential behavior, and here electrons screens out the field of the external charge. Yeah, that is our it is very reasonable, and also then that's why we can think about that electron solid can be regarded as a free electron approximation, because and the real potential is very weak.